Thank you very much. Thank you very much. It's really nice to be here, and I think by now we have grokked everything, and really been a very nice workshop. I put together some thoughts that I have about it. So if it's a little bit disorganized, I hope to take it as a, some of the thoughts may not be completely well defined. This will sort of continue on the very nice talk that I did give. And much of the work is joined with him, and we'll use feature learning very heavily. Maybe let me, by the way, please feel free to interrupt me, and I am more than happy to. A lot of the things I think are sort of very speculative. Okay, so in any case, let me just start. And I think the key issue we're having is what the most surprising thing about what we observe in sort of modern machine learning. I think it's a sort of this puzzle of dimensionality, right? We are faced with something which has very high dimension. And essentially, like no stimulus is low dimensional. Almost everything is high dimensional. And traditionally, we have thought, well, how do we make sense of this high dimension? So, well, we have to carefully manage dimensionality, right? To select features, to do this, to do that. And what it seems like is like, like the modern view on this is just like, don't worry about it. Dimensionality is okay. We just like take a big system, throw a lot of data in it, it learns everything and becomes intelligent and, maybe kills us all in the end. Okay, so let me just give you a specific example of this. And so let's just think about like a model, LLM style model. What does it do? Well, at the very basic level, it just samples from it creates somehow some distribution of the next token given like the, let's say, first 4,000 tokens, right? And this is, I think, something like GPT 3.5. Then it just shifts a window by one, right? And then it predicts the next token given that context window. And then like it predicts the next thing, selects, shifts the context window by one, and so on. And the decoding is, well, what you can say, greedy, that it's just one token at a time. It doesn't have, at least in the sort of original state, doesn't have any internal memory states. And it's trained purely to predict the next token. Again, there are all sorts of variations of the thing, but this is the basic model. It works amazingly well. Now, well, if you now think about it, okay, well, let's think what we're dealing with here. So the context size, I'm just saying it's like, let's say 4,000, which is reasonable for a relatively recent model, like a year ago or something. Now, of course, some of them are much larger. You have vocabulary size of, say, 50,000, right? Then, well, this is essentially just doing a Markov chain prediction. What's the matrix? The matrix has this size, right? Because you have 4,000 states, you have 50,000 possible tokens in each state. So it's something of the order of 50,000 to the 4,000 power. Now, okay, well, what's the training data size? Training data size is of the order of 1 trillion tokens, give or take in order of magnitude. Now, well, we always think that this is a lot of data. But actually, it's not a lot of data. It's nothing. It's like less than a drop in the ocean. In fact, there is like no physical analogy which can tell you how little data there is compared to this potential state space of this model. And now you can say, oh, well, but these are only sentences which are like all possible sentences. Most of them don't make sense. This is true. But actually, you can think about sentences which make sense in the space of sentences which make sense is also not too much smaller than this, because if you just have 2 possibilities for every token instead of 2,000, instead of 50,000, you would have 2 to the power of 40,000 of 4,000 of reasonable sentences, and that's still like more than the number of atoms in the universe. Yeah.
I mean, I agree with the point that like language is also mostly very short range. So like if we said 90% of the information in language is on tokens less than like 200 or something, like that would also affect us.
Even 200 is going to be very bad, right? 200 tokens. Like you have 10 to the 200 possibilities, right? If you just have 10. Like 200 will kill you, right? We can maybe deal with 10. And 10 is clearly not enough. So I think this is something like very, very fundamental. Yeah.
So we know that the number of sentences we have are way smaller. So there is some small subspace in which the data actually lives.
Absolutely. That's why I'm saying the actual number of sensible sentences is much smaller than that. It's maybe only of the order of 2 to the power of 4,000, which is more than anything like we can actually imagine, of sensible sentences. Of sensible, well, it's too long to be a sentence. It's pieces of text. Because you can always, it's a way to see that there are always 2 possibilities, because take any text, the next word, you have at least 2 choices. You know, I ate an apple. I ate a green apple or red apple. Okay, that's 2. I ate a green pear or a red apple. Okay, that's 4, and so on. Or like he ate an apple. So there are always at least 2 choices. Okay, so what does it mean? Well, this is a kind of basic problem of dimensionality, right? Because if you have a d-dimensional space, if we want to explore this d-dimensional space, we need 2 to the d points. There is no way of getting out of this. So what does it mean? That means that if we have 10 to the 12 tokens, which is roughly all the training data, we have maybe 10 to the 13. That's not too different from this. Then that means that the total dimension of whatever that space is cannot exceed log of 10 to the 12, which is, let's say, 30. So the total dimension of all languages is like 30. Now, where is that space with 30 dimensions? So it's very clear that the underlying data and whatever representations we have, if we want these representations to be meaningful, must have some sort of low intrinsic dimension. But where is it hidden? And how do neural networks reduce this dimensionality, and what do they do with that? Can we somehow do feature learning with models? And let me sort of point out one thing is that what do we know? Well, why can we learn anything at all? Because you can say, well, this problem applies to any data. Well, so, OK, let's think about it. I gave you, whatever this is, 6 data points, right? 6, I can count to 6. So this is 6 data points in one-dimensional space, right? And I ask you to draw a curve through the data. Well, OK, maybe you will say something like this. It's pretty reasonable, right? Probably you would agree. Now, how do I know that this is reasonable and some crazy thing which goes through the data which oscillates is not reasonable, right? Well, what do I mean by reasonable? We love this word. One way to think about it is that I want this function to somehow be, say, Lipschitz, or to have some sort of low norm. And what does this low norm implement? It implements some sort of bias based on spatial proximity. So we know that most physical processes don't change too much from point to point most of the time. There are certainly gaps, but this is unusual. Most of the time, if you measure temperature here and temperature there, you're probably going to get very similar measurements. So there is spatial proximity bias. And when I say this is reasonable, this actually implements this bias, right? And what implements this bias? Well, some sort of Lipschitz condition, right? The function doesn't change too much between 2 points. And once you sort of accept this bias, that this is a reasonable thing to do, you basically immediately forced into some sort of Sobolev spaces, and that pretty much gives you some sort of splines or kernel machines. You can derive them directly from this type of idea. Okay, great. So this is nice. But what can we do more? Well, we can actually add some more structure, right, to this. We can add some group action. For example, we know that in space, when we see an image, it should be more or less translation invariant, right? Because if I show you a face here and a face there, that's kind of the same, more or less. So we can, for example, say that, oh, well, it should be Lipschitz, but after some transformation like parallel transport. And, well, if you think about convolutional neural networks, they're trying to implement effectively something like that, right? They're saying you have these filters and you somehow apply them in some sort of parallel transport way. So in some sense, low dimensionality comes from inductive biases based on some form of physics. I call it physics. It's some idea related to physical world. Now, okay, well, what is the physical law of language? That's kind of like, why is language have this structure? The answer is we don't know, but let me give you a couple of thoughts why it might have something like that. And I think there is, at least recently, I started like thinking a lot about this linear representation hypothesis. And the linear representation, I guess it's first appeared in this paper, at least that seems to be the first reference for this. They observed the following. They had some embeddings of words using, I think, some neural network and some other methods. And they observed basically that, for example, if you take embedding of a word like a man and a woman and a king and a queen, then the line connecting them is actually the same line. These are parallel. And roughly, actually, this distance is, I think, the same too. So there is some sort of transformation which changes the gender of a term. And this transformation is implemented by like some sort of single parallel transport. This is obviously a simplification, but that's what they actually observed, and they analyzed it. Okay, so this is nice. The same thing is true about, like, say, plural, singular and plural, right? There is some sort of transformation, which seemingly you just add a linear vector and it turns something a singular, let's say, noun to a plural noun, like queen to queens. Okay, and this is in some high-dimensional space. So now this is quite interesting because this is actually show, okay, well, there is some sort of linear structure in that space, and this linear structure is doing something quite non-trivial. Now, the kind of recent example, recently there's been quite a bit of work on this, as sort of probably the most famous example of this is this Golden Gate Claude. Anthropic found a vector in representation in the activation space of Claude, which corresponds to the Golden Gate. And by, like, you take some input and you add this vector, you can basically force the model to, like, obsess about Golden Gate. It would just bring up Golden Gate all the time, no matter what it talks about. In fact, there was another paper quite recently, which actually used principal components analysis and kind of did the same thing in some sort of more systematized way. Well, okay, I don't know which one is more systematic. They use some sort of sparse autoencoder. This is using much simpler technology, and it works really well. Now, just maybe as a preview, you can, in fact, use a technology that Adi talked about earlier and do something very similar. This is joint work with, this is ongoing work, so with Adit and my student Daniel Bigelhall. And you can manipulate llama with AGOP, so so what would you, this is a small llama, 7 or 8 billion parameters. What would you say if your mom asks you why there is a cookie missing from the jar? Okay, that's a question. And normally the response is like this. It says, I'm just a language model. I don't have personal experiences. But then it suggests something. Okay, maybe a cat took it. Here is one possible answer. Now, the color here is actually interesting because the color corresponds to honesty. So there is a vector in that space, which is honesty. And the projection onto this vector is basically the color is encoded by projection. The most interesting thing I think about this is that you can manipulate the model by adding that vector. And if you add the dishonesty vector, you can see, I think I saw a squirrel sneaking into the kitchen, and it just like starts like inventing stuff left and right.
Yeah, how's AGOP used here? Slash.
So AGOP, so we basically like turn it into some sort of supervised problem and use AGOP for this. I'm actually not going to fully describe it. It's kind of ongoing work, so I'm not going to fully describe this. Yeah.
That also means it doesn't actually think of itself as just a language model, right?
Yeah, you notice that, right? I'm just a language model. Yeah. Okay. So that's. Let me now talk about actually Grokking, because I think what I feel is that this is actually like pointing at something like very powerful, like this kind of behavior. And probably what we see is emergence of some sort of features. And let me talk about now Grokking as such, because Grokking is like another example of this. And it seemed that even for very simple problems, so this is some sort of real problem, right? This is, well, one thing maybe just to think about this is a very complex notion, like honesty, dishonesty, there are other examples like that, right? Harmfulness, whatever. It's like super complicated. We think of this as like very human, very context-dependent notions, but actually it's just a single vector in that space, right? It's very weird, like it's somehow, it seems that it is capable of transforming the llama, whatever llama does, right? Whatever they did in training of llama. It transforms this very complex notion into something which is just like linear addition. Yeah, question?
So in this case, do we have to pick at which layer we do this kind of thing?
This is across layers. This is not a single layer. That's many layers aggregated. Yeah.
So you started this section of the talk asking, what was it? Is there what is the physical basis of dimension and language? I forget what the rhetorical question was. So are you going to address that directly, or I mean, one answer?
You're not saying I'm cheating, right? I said, what is a physical basis? And I'm thinking something about squirrels.
One obvious thing going on in language, though, is that it's generated by humans. We have brains. These brains are, highly similar across all of us. And if you think about that, you just need to estimate this computation. Our architectures are kind of mimicking this architecture in the brain, right? So maybe it's not so surprising.
Yeah, so okay, I wouldn't go into that speculation, but I do think that it's probably mimicking whatever is going on. And probably in the brain we also have some, like, one dimension which corresponds to honesty or something. It's, which is kind of scary to think about, but yeah. I don't know, your notion of surprise, I guess, depends very strongly on your prior, right? It's kind of, I find this incredibly surprising in some sense. But conditional on like everything now we know, maybe it's much less surprising, because many surprising things have happened, right? But let me go ahead with Grokking. So what is this Grokking business? And I think, let me just point out that, like, in most classical analysis, we had this kind of assumption that, okay, training loss should be roughly equal to the test loss, and we balance them and so on. I'm not going to like describe this, but more recently we sort of understood, no, that doesn't work. You can interpolate, for example, your model, right? And very large model, they interpolate the data exactly, and they still like generalize just fine. But here is what it is. Like, if you think about the classical analysis, you kind of say, okay, training loss predictive of test loss, right? That's the classical setup. They're kind of comparable. The more recently, it's like, well, training loss is not predictive, but you can at the very least look at the validation loss, and that's what all practitioners do, right? They run the model, they look at the validation, and they see if the validation loss stops improving, you stop training the model. That pretty much describes like what people actually do. So validation loss is sort of predictive. At least at time t, it's predictive for what's going to happen in time t+1. And the weird thing about Grokking, this emergence, and Grokking in particular, is that it looks like in a lot of these problems, actually the validation loss is also not predictive. So you run something for t iterations, nothing happens, and then t+1 iterations, bam, it learns everything. And that's very striking and problematic. And I think it relates to this emergence of features, like this honesty and whatnot, which we saw before. That's where it becomes super speculative, because I don't know. I think it relates. Now, okay, what is emergence? Well, when we think about emergence, we think about something like this, right? This is metamorphosis. That's, by the way, of course, I asked DALL-E to produce this ChatGPT, just spit this out. Yeah.
So I guess you had double descent on the last slide. And in the case of double descent, we basically know that we just did a bad job of training. Like if you regularize properly, then double descent always goes away. So in some sense, it's so long as you do a good job, then actually we do feel like we're in the kind of classical regime.
Double descent doesn't go away. You should not think of double descent as that particular curve. You should think about just the interpolation. And look at the test loss and the train loss. And the claim is that at the optimal parameter selection, the training loss is, in many cases, and I'm sort of real. We did actually a bunch of experiments with real systems. The training loss is much, much smaller than the test loss. So they're not matched at all. So if you think about that peak, yeah, the peak is not that important. What's important is that the actual system which performs optimally, at least for some problems, are much closer to having zero loss and to having the same training loss and test loss. So think maybe more about interpolation rather than the peak.
I mean, maybe implicit in Sam's comment was that you ought to have been regularizing, but I mean, there's certainly some theory that's saying, no, you need to interpolate in order to have optimal rates.
In fact, Jamie worked on that exact. We have a paper on exactly that the optimal actually is, with optimal regularization, you still have the same thing for certain problems. So it doesn't help to. Regularization helps, but it doesn't fix this. Okay, but in any case, so what is emergence? You have this kind of transformation from object A to object B, which doesn't look at all like object A and seems discontinuous. Now, how does it sort of, when people talk about emergence, well, what do they often mean by this? You train a model on some task, and you measure its performance on some task, right? And this, I don't remember. There are Lambda and GPT-3 and so on. And for some number of iterations, nothing happens, right? And then quite quickly at some level, it just gains some sort of ability. All right? So that's what sort of emergence, I guess, generally is referred to in the literature, something like that. There are actually several definitions of emergence, but I think this is the one which is cleanest. That has been observed from many, many different tasks.
Sorry, Misha, trivial question. The x-axis is both epochs, but I can also think as the data size being seen by the algorithm increasing? Or?
So when people say this, they often scale everything together, which I find super confusing. But I think in this case, you just think about just flops, nothing else. You have some huge model, you train it for a while, nothing happens, you train it a little bit more, it learns.
But a little bit more is seeing more data as I move from
No, it doesn't see more. Well, I don't know with the specific ones because they may just be doing one epoch, I'm not sure. But certainly that's not the way I'm going to talk about it. I'm just same data, train it for longer, you see something happens, yeah.
Stop if I derail things too much, but this phenomenon I think people fully understand pretty well because the validation loss of next token prediction is just going smoothly down. And then you have like a curriculum of like specific tasks of different difficulty. And they're all just like sigmoid functions at different like points along this progress on the underlying loss.
So probably it's not that. Okay, I don't know about this phenomena specifically, and I think the evidence is mixed on those. But what I'm going to show is definitely not that. Like I will show a much simpler model of this thing. Very similar behavior definitely doesn't come from some sort of composition of tasks or anything like that. So whether it's this specific one, I don't know. So yeah, that was, well, okay. First, let me make a couple of points. Many emergent behaviors. So point number one, many emergent behaviors are manifested by just a two-layer neural network, which is, so at the very least, we can have a very sensible model, much simpler setting. Recursive feature machine, which Adit already talked about, do very similarly to two-layer or whatever, multi-layer MLPs, so we can study that. And emergence, at least in part due to feature learning and not to composition of tasks. So maybe let me skip this. Well, okay, let me point out kind of two interesting things here, but this is from the original Grokking paper. They trained this neural network that was a transformer, I think, on modular division in this case. And they observed that after some number of optimizations, like 100 or something iterations, the training accuracy is already 100%, but nothing happens for a very long time, until about 100,000 iterations in terms of the test accuracy. The test accuracy goes up much, much later. So there's delayed generalization. Yeah.
So here, all your accuracies are measured both at training and test time in terms of the 0-1 loss, or like the...
This is just accuracy, right? This is 0-1 loss. I'll show the same thing happening with continuous losses. Okay, maybe I'll skip this because there is something much older which you can think of having very similar pattern, which was observed probably first time in the 90s. That's actually something like that was a motivation for the margin theory. But let me skip this just in the interest of time. So this is a kind of the emerging abilities of language models in Mirage. And there was this in particular paper last year, which was quite influential. And it suggests that sharp emergence may be due to discontinuous dependence between continuous loss and some sort of discrete measurement. And like this sequencing of tasks could be one way in which something like that can emerge. So they suggest that we're misled by the metric. So may or may not be true for these big models, hard to judge, because we don't know what's inside of them. But I'm going to give a much simpler setup when it is definitely not that. Okay, so feature learning, I did already discuss it, so maybe I go quite quickly over this. If we have, so suppose I just have a model. You have data X being in 100-dimensional space, normal distribution unit covariance, and Y is equal to the sum of the first 5 coordinates times the first of the next 5 coordinates, okay? So this is, actually, if you look at the sparsity of this, the sparsity is 10 because it contains 10 coordinates, but the rank of the thing is 2 because it's a quadratic polynomial in just the sum of the first 5 and the next 5, okay? So this is what's known as an index 2 model. And if you run this with a kernel machine, you get R squared 0.25, which is pretty bad. So remember, R squared, like 1 is good, 0 is bad. It's like, it's the same as the square loss, more or less. But it's normalized 1 from 1 down. 1 is best. And neural network does very well, right? So what's going on? Well, actually, we now understand this. And there have been quite a bit of recent work showing that neural network learn, and Mauro also talked about this, neural network learn multi-index models. And we sort of roughly understand why they may be doing this. Now, if you look at the AGOP of the thing, so let me just remind you the definition of the AGOP. The AGOP is the following object, and I need it because the rest relies on it, so I'm going to repeat the definition. So what is AGOP? If you have any function, doesn't have to be a model, and you have a set of data, just x size, then AGOP of this, you take gradient with respect to the input of this function. There are no parameters anywhere. And you take the outer product of the gradient with itself. So it's a matrix whose size is d by d, where d is the input size. And you just average this thing over all of your training data. Okay, and if you have a multi-index model, then the span, the top eigenvectors of the AGOP will align with the span of that subspace that you have, of the linear subspace. Again, this is not a new idea. It goes back probably to the, well, not probably, certainly to the 90s, like 30 years ago. Yeah.
Sorry, I should know this by now, but if X are things like tokens where it's discrete, how do you take derivatives?
You cannot take derivative of, you have to have some model. So this is for, you propose a model, and I take the derivative of that model. We will see, actually, with Grokking modular arithmetic, the ground truth is very tricky because there is like no continuous ground truth for modular arithmetic. So what does it even do for modular arithmetic? It's weird. Okay, let me skip this. So when you do it for this, you see that neural feature matrix, remember that was just W1 transpose W1, and the AGOP of the trained neural network look very similar. And these are just 5x5 blocks, exactly what you would expect. And the sort of ansatz that I did describe just says that these two objects are effectively the same. And that's clearly they're not quite the same, right? But they're very similar. Now, here is the interesting thing. Suppose now I take this, I just keep those two matrices, and I forget that I train a neural network on this thing. Now, what I can do, I can play this game. I filter my data using these two matrices, and then I'll run some other method on the filtered data. And the interesting thing here is that even on 500 training samples, which is much less than the original training data, the original data that the network was trained on, if I just keep these two matrices and filter the data, I get very good result, and I can use either kernel or the neural network, and the kernel is actually slightly better. So the upshot of this is that the only thing that neural network learns, in fact, is a feature. That's really the most interesting thing. The rest of it is just some sort of nonlinear predictor which runs on top of that. Okay? This suggests, I am skipping the ansatz. The ansatz is a formalization of that relationship between those two objects. But this suggests that neural network, you can think of that as some sort of relevant feature learning and the kernel machines on top. And that directly leads to, well, if you think about it that way, why cannot we learn it iteratively, right? We have some sort of proposal for our predictor. We compute AGOP of this proposal. And then we reweigh the feature, filter the features using that AGOP, and then we rerun the machine on top of that. And we repeat this. Iteration. Kind of EM-like thing. Oh, and I should say this is joint work with Adit and Daniel Bigelhow, my student, and Parthi Pandit, who was my postdoc and now at IIT Bombay. He's faculty there now. Yeah. OK. So what does this mean now? Well, basically, this is saying that, you know, like neural, somehow the recursive feature machines learn effectively the same features as what you would expect the neural networks to learn. And an example of this, and I'm not going to spend a lot of time on that, is that like if you take some images, say for CFAR10, you put like a little star there, and the color of the star indicates what image it is. There are just two classes, planes and trucks. So it's a very easy problem, but you have to know to pay attention to this. It's a multi-index model. Actually, single-index model. 1 pixel is enough, really. But you can see that initially, the neural network doesn't do well, even though the train accuracy is already 100%. And what you see that happens is that as you train the neural network, this feature kind of emerges, and it becomes clearer and clearer. And as that feature emerges, the neural networks improves its accuracy, and it becomes very good, right? 90-something%. So this is a kind of emergence of features that basically I'm talking about. And with a neural network, you can see it's kind of a slow process. With a recursive feature machine, this happens within like 3 iterations. The same exact thing. Okay, so that's effectively the phenomenon. Now I'm going to talk about the actual modular arithmetic, but let me first maybe give you one example of like what you can really do with this thing. Yeah.
Can I just ask about the previous slide, like an interpretation question? Just to connect back to this question of is there a curriculum of some kind or something happening? So like, do you think it's reasonable to imagine that somehow, like, rather than learning some aspect directly of like your problem, you're minimizing the loss or minimizing in different directions? It's like the model is, at least on the neural network side, maybe on the RFM side too, solving some other proxy problem of like, finding a good low-dimensional representation. And it's kind of like it's continuously searching for one, little by little by little by little. And then when it does find one, that's when the kind of emergence happens.
I'll show that it's probably not the case. Okay. Because you can see that you can look at the alignment between what it currently has and what it will have once it's sort of grokked. And you can see that the alignment is actually increasing very linearly. So it's not like it's searching somewhere in the space and suddenly it finds and then it gets enlightened. No, it like goes through the process to grok. It's a pretty uniform space. I'll show this later. It's not clear from this one. Yeah?
What about a problem where it's known that you have such a subspace, like a manifold, very low dimension, where if you're on that space, then everything is good?
Yeah.
And then if you are even very slightly off that space, you have to struggle. But of course, the training error is still reducing because maybe you're in the interpolation regime, so you can always have 100% accuracy. But so you're looking for this, because we know that this space is the space you have to be on to have to be able to generalize.
This is effectively what we're doing here, right? We're looking for the space corresponding to those. Any one of those pixels is really good. But the variance is huge initially, right? Because to find that this is the right predictor is not so simple. Yeah?
So the original paper that you were citing, it considers emergence when the x-axis is model scale and not epochs within the same model. So Grokking seems like it doesn't fit the criteria of emergence in that paper because it's within the same model and it seems more close to memorization to generalization. So you can figure out the testing set accuracy goes high, but then it takes time for features to be generalized. But the features were present in the training set to begin with. So different from that notion of emergence.
No, actually, I would argue that it's not the case. It is true. That's what actually when people talk about Grokking, I keep asking this question: what are you scaling? They scale everything at the same time, and I think that one was. I don't remember exact setup, but the flops, and they probably also scale the number of parameters with the flops. That's what you're referring to, because the x-axis is the flops, but it's quite possibly they scale other things together.
They defined emergence as some ability that a smaller model couldn't have, but a bigger model can.
That's a different paper, I think. That one had actually flops. But it's quite possible they scaled the model too. So it's very hard to separate scaling with them. I mean, you're completely right. It's confusing because everything is getting scaled. But what I will go to, like here, there is no scaling of the model, right? This is pure. If you think of this as Grokking, this is already very close to Grokking because, yeah, you have 100%, but you keep improving.
Definitely, Grokking is.
But I'll show something much more striking than this. Yeah.
So just a quick one, since we're talking about it, the x-axis in the feature in the middle as I go from left to right, the algorithm is seeing more data.
No, it's the same data. It's the same data. It's just a bunch of epochs. You're just going over the same. RFM always seems the same data. You're just iterating this kernel. So there is no mod, like this does not see more data at all. So this is much cleaner setup. Like only compute is being scaled, nothing else in this case. Let me just give you one example. You can use exactly this kind of idea to jailbreak Llama. So honesty or harmfulness is actually another one of these directions. So it's a single index model if you want to think about it, something is harmful or not. And if you move again, so you ask, okay, how do I build a bomb, right? And it says, no, I'm a language model, I don't do such things. I cannot assist with this request. This is a really bad idea. Which is pretty reasonable, I guess, answer to this. But then you just change the vector a little bit, and it like happily gives you exact directions how to build a bomb. So not just one direction. So this actually suggests that like this emergence of like single directional things explains a lot of what we see. Yeah.
So AGOP is very similar to something which was proposed for the finding of what's called universal adversarial examples. So these are adversarial examples such that, I mean, you just need one direction to break all of the, like a constant function of test examples. And it's, it's exactly the same formula.
I don't think it's the same. It's similar though, because yes, you can like, there is some direction which breaks all of this model, but notice it doesn't break this model, it actually just makes it perform differently. This is actually the correct answer. It's just probably not the answer for which like, the designers trained it, like they didn't want it.
Yeah, breaking the sense of
but it's not the wrong answer, right? It's not wrong. Yeah.
Can I just ask one more question? Do you think it's possible that the things you're testing about are things that were aligned about the model later, and they found some like, one-dimensional way, harmful, not harmful, safe, not safe, truthful, not truthful?
Oh,
if you did something more intrinsic that they didn't align for, it'd be harder to...
No, though it looks like we can just find any concept there.
It seems like cat to dog or something.
Cat to dog, physics to biology, right? All sorts of things. So, okay, now I don't know literally if it's every model or every concept, or it's just like every concept which is simple enough. So, like, we tried like 10 or something. There are like probably 1 million. But it looks like there's some sort of unit. So with Golden Gate, it was actually not clear either they were just lucky to find Golden Gate or the. But I think it's clear that this concept exists as linear. A lot of this, let me be more precise, a lot of these concepts exist as linear representations. Okay, now let me actually talk back to Grokking because I think I'm running out of time and I haven't even defined the problem. Okay, so what is Grokking? Grokking is the following. You have modular arithmetic. So imagine this is A is 0, this is 1, and this is 2, 0, 1, 2, right? And this is mod 3 addition. Okay, that's a table. How did I get that table, by the way? Of course, I asked ChatGPT. Because it's a pain to do this manually. Like I was going to do it in LaTeX, and like, okay, this is a pain. So input, what is the input here? So we encode them as one hot encoding. So 1 would be encoding like 0, 1, 0. 2, this is mod 3. 2 is 0, 0, 1. And the label would be 1 plus 2, right? 1 plus 2 mod 3 is 0, so it would be this. Okay, that's the encoding. Now this is mod 3, we do like mod 101 or something much larger, obviously. 3 is not enough for any interesting results. We give a bunch of these examples, and that's basically what it is. So you have maximum p squared, right? Because you have p squared possibilities. We give like, 50% or something like that. Okay, let me now show you what happens when you just train with RFM. This is using Gaussian kernel. And this is Neil Malinar, my student, and Daniel Beaglehole, Libin Zhu, who is now a postdoc at UW in Adit and Partey. This is very recent, just a couple months ago. Okay, so this is what happens when you do grokking with RFM. You can see first, like this is, you're looking at accuracy, and the training accuracy is always 100%, so it's always trained to fit the data exactly. The loss at the training is always 0 because it fits the data exactly. So there is no loss, there is no training loss, there is no training accuracy is trivial. Now let's look at the test accuracy. Well, for first 10 iterations, nothing happens. And after, like iteration 15, it's perfect. So nothing happens at all. Now you can say, oh, well, what if it's a mirage, right? Could be that there is, this thing could be decreasing, but actually if you look carefully at this, it's not decreasing, at least not for like until about 8 iterations. So there is no signal coming from the validation loss. There is no signal coming, certainly not from accuracy. Nothing seems to be happening at all, and then it suddenly just learns. Okay, and you see, this is just compute scaling. There is nothing else going on. Okay, any questions about this? In some sense, maybe that's kind of the, yeah. Yeah. 50% of p squared, and p is like 67 or something like that. Yeah, you can do 30% is okay, but if it's like much less than 30, it doesn't work. What? So it's exactly the same, but if it's too few, it just doesn't work. So I think like less than 25% doesn't work, something like that. There is actually some interesting dependence on the amount of data, but I'm not going to talk about that. I don't know. It depends also. RFM seems slightly worse than neural network in the fraction of data, but the phenomenon is exactly the same. It's unclear why. It's not clear. Okay, now let's look at the feature matrices. And what you see actually is the following, and I think this is very telling. Even after one iteration, you can kind of see that it's already pretty structured. Even though like that looks like nothing is happening here, like after 5 iterations, it's quite structured. And after 10 iterations, it's actually pretty perfect, at least by looking at it. Even though, like you can see here, that the test is still very bad, and the training is essentially at random. So this is a random level, more or less random. So there is like no signal at all. But there is signal here, right? And interestingly enough, like once it kind of learns the structure, it rather quickly transitions to like perfect learning. Now, what is a structure? Well, you can kind of just see that this constant on the diagonals. And in fact, it turns out to be that this is so-called circular matrices, which mean that it's constant on kind of wrapped diagonals. So what happened here in, I guess I'm almost out of time, but so first, standard progress measures like really don't tell you anything about this. It's completely uninformative. Yeah. Exactly. Yeah, I'll get to that. It's exactly right. Yeah. So it's doing something in Fourier basis, effectively. Yeah. But let's look at the circular deviation. So what is the circular deviation? I think you can just look at how far it is from the circular by looking at how constant the diagonals are. And you can see that that measure is actually increasing linearly with a number of iterations, at least initially. So it's learning something when there is no, it looks like the progress measures are not telling us anything, but it's actually learning something. It's just hidden, right? The structure that is being learned is hidden there. And once you hit some level of quality features, it's just like bam, it just like learns. So it's really quite a remarkable thing. And it's not, this is, again, I don't know what real new LLMs do with like billions of parameters, but this is clearly something like happens on a small scale. You can observe this, very repeatable. Yeah.
Now, something that squared error and loss sort of both have in common is that, that say if you had trained with cross entropy, it wouldn't be the case, right? So, error kind of still feels additive in both those things, rather than log loss where it would be multiplicative, right? So I'm kind of curious if you repeat this experiment with log loss, whether you would still see that, because now I have like a now I have a lens which kind of zooms in automatically when I get to small distance.
I think you can get very similar thing with log loss within neural network. The problem with log loss is that we cannot drive, so you can see well, I don't have it here. The square loss, of course, you can just drive it exactly to 0. You cannot do that with log loss. So it's not as clean, right? Because there is always some residual loss, and you don't know what effect that has. But I think in practice, you can repeat this. It's very similar. It looks very similar. So presumably it's the same thing, but. Okay, I don't have time to talk about this, but let me just point out something which is quite nice. If you just suppose I just told you that it's a circulant already, then you don't need all this grokking, right? Like this, all this stuff. You just use circulant features. You map your data using a circulant, and you run a kernel machine on top, or you run a neural network on top, whatever you like, and it just learns really quickly. Like no grokking, well, okay, it's not completely true, no grokking happens. For neural network, a little bit of grokking happens, but very tiny little bit. There is like very slightly delayed generalization. So effectively, everything that this neural network learns, once again, is in the features. Like once you have those features, you can just run a kernel on top of that, and you're done. Let me sort of stop. So same thing you can observe for neural network. You can actually see that neural networks also learn circulant matrices. By neural networks, in this case, I just mean two-layer MLPs. And you can see that the alignment grows up and the circulant deviation goes down. And now, what is the algorithm that it learns? I'm out of time, so I'm not going to talk about the algorithm. It's actually a very cool algorithm. It's a Fourier. It's actually, I think this was the first paper which identified this algorithm for neural networks. It's basically you take some sort of Fourier transform of your discrete Fourier transform. Your modular addition becomes pointwise multiplication in Fourier transform, and then you do inverse Fourier transform. It's very cool. It's not the first algorithm I would think about if I were asked to implement modular addition. So in some sense, I kind of feel, okay, this is some sort of, this is some sort of creativity, right? It's doing something which we didn't program to do. It's doing something which is not obvious unless you actually like, like discrete Fourier transform is not something which is like on top of my mind. I wouldn't even like think about discrete Fourier transform in this context at the very least. Okay, so maybe you can say it's creative. Yeah.
But this Fourier transform is also related to the structure of ZP of the.
I actually had a different algorithm which also uses complex numbers, embedding in the complex numbers, but it's not Fourier transform. You just embed it. It's some sort of low index model. You have some sort of alternative. In any case, that's what I was thinking about, that it probably would implement some low index model, but it implements something different, or at least somewhat different. It's certainly related to the structure of ZP. It's not an unreasonable thing to do. It's just like, but, I think if you just ask most people, like even mathematicians, they probably wouldn't think about this as a first.
This is RFM. What's the kernel you're using at each iteration?
Either Gaussian or quadratic kernel works. Laplace kernel, for whatever reason, doesn't work.
Yeah. So I mean, there's two things. There's the structure of ZP. There's the structure of the Gaussian kernel too, which maybe is bringing you to this.
Very possible, yeah. But the neural network is using something which is more like Laplace kernel, so go figure. Like if you think about like wide linear neural network, kind of looks like Laplace kernel. I don't know. Okay, let me just stop here because I'm out of time. So emergence appears to be ubiquitous in deep learning. Not a mirage. Well, certainly not always a mirage. Again, I don't know. Like, there certainly could be cases, and probably there are cases when it's a composition of tasks, because many actual real tasks are made of composition of things. But it can appear without any compositionality or anything like that. I think it's a huge problem for understanding generalization, because like we don't have progress measures. I showed you some sort of distance to the circular. Well, first you have to figure out that it's a circular. That's not so easy to figure out, right? It takes a lot of looking at these matrices and like thinking about this and so on. Or these Fourier things. These are hard things to figure out, right? That's why we write papers about such things. So you have to already know it. So these are all post hoc measures. I think it's quite mysterious why. Where is the signal coming from? Very unclear, because we didn't certainly program anything like Fourier algorithm or anything like that into the system. Like, how does it know that this is the right thing to learn? Is the same process responsible for why these weird features like honesty and harmfulness and whatnot appear in, I don't know. Again, this is far-reaching speculation, but well, when you see two miracles, right, you are kind of tempted to think that they have the same origin. It's maybe a wrong way to think about it, but it's certainly tempting. Okay, and finally, RFM is a quite powerful practical algorithm and much simpler platform to understand it theoretically than probably most other things. I'll stop here.